We present Strumming to the Beat, audio-conditioned contrastive video textures. Given an input video, we synthesize a new video that matches the conditioning audio. We first consider unconditional video texture synthesis using visual features only and no audio. Our approach is inspired by video textures, a classic non-parametric video synthesis method which converts a single input video into an infinitely long and continuously varying video sequence by stitching together parts of the input. Given this 3-second clip of a candle flame, this method synthesizes a 10-second clip by finding alternative, plausible transitions in the input video to produce different yet dynamically consistent videos. The red bar at the bottom indicates the part of the input video that's being played. However, classic video textures uses Euclidean pixel distance as a similarity metric between frames, which makes it brittle to videos with irregularities and chaotic movements, like dances or musical instruments. For example, given this video of a person playing a guitar, the classic method produces jarring transitions. In this work, we investigate contrastive learning approaches for graph-based sequence generation. We propose contrastive video textures, a non-parametric, learning-based approach for video texture synthesis. Our method uses learned feature representations and a distance metric to compare frames, and produces a smooth video with seamless transitions. The red bar at the bottom indicates the part of the input video that's being played. Here is an overview of our method. Given an input video, we extract overlapping segments from it. Next, we learn feature representations and a distance metric for these video segments by fitting a bigram model. Given a query segment, the model learns a representation that is similar to that of the positive segment and dissimilar to the learned representations of the negative segments randomly sampled from the rest of the video. The model is self-supervised and is trained using contrastive loss. During inference, we start with a random segment and use the fitted bigram model to compute the edge weights to the remaining segments in the video. To introduce variance in the synthesized textures, we scale the temperature to modulate the sharpness of the softmax distribution. We denote higher weighted edges in green and lower weighted edges in red, and the thickness correlates with the probability. We randomly traverse along one of the higher weighted edges to reach the next segment. Both segments are then appended to the output and the process is repeated, with the second segment as the query.